Okay, so thanks very much to the organizers for putting this together and giving me the opportunity to talk here. It's always a very great pleasure to be back here at ICTS. Sorry for the slightly croaky sound, okay? Seem to have gone down with a bad cold and cough. Okay, so this talk, the collaborations, okay, I'm going to talk about thermodynamic costs for steady state erasure. You'll see what it is shortly. My collaborators on this particular talk, actually this work isn't really fully finished, so it's sort of work in progress. And my collaborators are Deepak Gupta and Christian Olsen. Deepak is someone maybe many of you know, was Sanjeev's PhD student from about 5 years back, and he's been around a bit, and now he's a Humboldt Fellow at Berlin. And Christian was a postdoc at Nordita, and now he's a postdoc in Düsseldorf. But this work is built on earlier work, which involved, besides these two, also Francesco, who also perhaps many of you know, who was Gregory and Satya's previous PhD student, and is now at Oxford. Okay. So, the base of this talk is this phenomena of resetting, and I should say I'm mildly surprised that we haven't heard so much about it in this conference, but we did hear just a little bit from Shamik a couple of days back. Just so that we are on the same page, let me just say a few things about it. Okay, so this was a very simple model, incredibly simple model introduced by Satya and Martin Evans in 2011. You see the reference there, and then there is a recent review. I believe there is a book in the making. So the phenomena itself is extremely simple. It's just that, okay, you have a process, maybe just Brownian motion or whatever, and every once in a while you just put it back. You know, in this particular, the simplest model, you just put it back to the origin. It starts again, you put it back. Then it starts again, then you put it back. And that's it. Okay, that's basically it. So extremely simple. The time intervals before you put it back could be anything. Exponentially distributed is typically what you use, but it could be periodic, it could be some other distribution, it could be whatever. So you see that it's described by this kind of what we would call an over-damped Langevin equation. This is just the regular motion, this is you put it back. The regular motion, could, for example, could be just free Brownian motion, motion in a potential, or whatever. So this process develops a non-trivial, non-equilibrium steady state with a current. So it was interesting for that reason. You could take anything you were doing and then reset it, and you'd get something interesting, like an interesting non-equilibrium steady state. So that was one aspect of it. But there were other aspects which they also mentioned in this paper, and that is that it optimizes search in some way. So if you're looking at average first passage time to reach some target, resetting actually helps you, and there's even optimal reset rate that makes search the fastest. So that was a very interesting point. Then it turned out that a lot of processes in biology and ecology, etc., could be thought of as things with resets. So that was even more interesting. So there were all these interesting aspects to resetting, which made this a very, very popular field of study. It still is. But our interest in this was that, okay, so it has all these nice features, so there must be a cost. See, there's no free lunch, so there must be some cost to actually, sort of implementing this reset. Okay, so how would you actually go about finding such a cost? Okay, so how would you sort of be able to quantitatively get such a cost? And when we talk of a cost, a thermodynamic cost, then we talk of something like a work. So then I have to think of like an actual mechanism that implements it, and then I say, okay, how much work did I have to put in to do this? But I could also think of it in a more sort of abstract sense, and I could think of it as sort of entropy produced or heat dissipated in the resetting process, even if I didn't know anything about what was implementing the reset, but I could sort of measure this change in entropy. Then so I could say something about the cost, the thermodynamic cost. And so this is a sort of, so when I say change entropy, so the resetting, so the whatever process you had, and before you reset it, it had some distribution. It was some probability distribution. After you reset it, it has some other probability distribution. So there is a change. You're sort of implementing a process that is changing the distribution of the system. There must be some cost, okay, an entropy cost. That is sort of a reminder, reminds us of this sort of, this Landauer erasure phenomena of information erasure. There, of course, it was bit information. This is not a single bit that we are erasing. Nevertheless, there are lots of analogies. In the same spirit, you could ask for a bound. So, so of course, different procedures you implement will have different costs, but is there a bound on such a cost? So that's a very interesting question. Again, very similar to the Landauer erasure problem. Now, when we are talking of bounds, there are some bounds, of course, that we know from textbook, from our first courses in thermodynamics. So remember, I said we are taking one probability distribution to another. If we were taking an equilibrium distribution to another equilibrium distribution, then we know that, just from the fact that the entropy, total entropy of system plus reservoir increases, the free energy for the system is defined like this. We immediately, the second law tells you that any work that you do has to be greater than or equal to the free energy difference. So that's just the simple, if you're taking an equilibrium to an equilibrium distribution. So basically the bound then would be the free energy difference of the initial state, of the final state to the initial state. And this was very nicely, so in the context of the Landauer bound, the free energy difference turns out is just the entropy difference, because the system, the bit before and the bit after, there's no change in energy, it's just a change in entropy. So the free energy difference is just the entropy difference, as was very nicely illustrated in this experiment here. So what they do is actually that they have this particle trapped in a potential. It's a kind of double well potential. In the beginning here, you don't know. The particle is somewhere, you don't know. So its entropy is like log 2, k log 2. And then you implement this procedure by means of which you sort of reduce the barrier, and then you tilt, and then it lands up there. So you see that this erasure procedure, this particle will land up there no matter where it was here. You didn't have to know where it was there. The procedure makes it land up there. You can do this in a finite time. You can do this incredibly slowly. And then you see that so this is work as a function of the time that it takes to implement this procedure. And you see that when you do it really very, very slowly, you get the k log 2, which is very, very nice. If you don't do it slowly, so the k log 2 was just the entropy difference between our initial and the final state. If you don't do it slowly, then the state, let's say you don't do it slowly, the state that you land up in, if you do it at some time, which is some finite time, is not an equilibrium state, it's a non-equilibrium state. So then how do you estimate costs in this? So how do you, for example, estimate this curve? Okay, that's the kind of question we are interested in. Of course, needless to say, the slowest protocol is such that it should be a reversible protocol. Then total entropy hasn't changed in our system. That ensures that that is really a bound on the cost. Okay, so now if you want to, so there's also, so as you see, there's interest in the bound, but there's also interest in this how the bound changes. Or rather, how the costs change when I do it in a finite time. In any experimental situation, I have to be able to do it in a finite time. And there's also, okay, so before that, maybe I should say that, okay, we talked of a bound between equilibrium, so the free energy bound between two equilibrium states, the free energy difference between two equilibrium states gives us a bound. What if I go from a non-equilibrium state to equilibrium state, or equilibrium state to a non-equilibrium state? What is the analog of that? And so here was some results. There were several results, but this figure is taken from this paper of Esposito and Vandenbroek. What they say is that, the analog of equilibrium free energy, there's a non-equilibrium free energy. And suppose I'm going from, I'm doing some procedure which takes me from a non-equilibrium state 1 to a non-equilibrium state 2. Just for simplicity, imagine that this non-equilibrium state is some particle in a potential U, and this non-equilibrium state is some particle in a potential V, and I'm somehow managing this change from this U to V in this time. What is, just like we have a free, like a free energy difference for, difference between equilibrium states, you have actually this, a non-equilibrium free energy, which is given by the, so look at this initial state. The non-equilibrium free energy of that state is its equilibrium free energy plus some information-like term, which is the Kullback-Leibler divergence of the state with its sort of instantaneous equilibrium state. So if I was in a potential U and I was in some non-equilibrium state for some reason, and then I switched off everything that was making it non-equilibrium, it would go to the Boltzmann distribution. And then I calculate this Kullback-Leibler divergence, and so what what some of these papers say is that this is actually a good definition of a non-equilibrium free energy, in the sense that it's a physical definition, and then the free energy, the work bound on going from this state to that state would then be the difference of the non-equilibrium free energies. Okay, so that's kind of interesting. And this delta F can actually be less than delta F equilibrium, because the difference of these Kullback-Leiblers could also, the Kullback-Leibler itself is positive, but the difference could be negative. So it's actually kind of interesting. You can actually show its consistent definition, given the definition of our entropy, system entropy as Shannon entropy, and etc. So you can show that this is a consistent. There's also more work. So this is still in the context of Landauer erasure. There's more work on Landauer, so this erasing bits in finite time. So here, for example, in this, in some of these papers, what they show is that, okay, fine, I get a bound. So let's say that it was a question of doing something non-equilibrium here and coming to an equilibrium state. Then this bound would be the non-equilibrium free energy difference. If this was equilibrium and equilibrium, like we said before, this would be the equilibrium free energy difference. This one, the time dependence, is actually also very interesting. There is a B, it seems to have a generic form, B upon tau. This B itself can depend on tau. Now notice that this B upon tau is actually related to the entropy produced in the whole process, because it's W minus delta and delta F. And this B is actually related to this thing called the Wasserstein distance that we heard the other day from Bhargavi. So this seems also rather a generic structure to this whole thing. Remember, this is still in the context of our Landauer erasure. And now I want to somehow understand what it is in the context of resetting. Okay, so what are bounds? So if I imagine, so remember that if I want a bound, I don't need to think of anything concrete like an experiment. But if I want to understand some kind of time dependence, then of course I have to have some experiment in mind which is implementing the procedure. Okay, so the rest of the talk is going to be about the resetting, a procedure that implements resetting, and how you would get bounds and how you might be able to get this, etc. As I said, it's still work in progress, nevertheless. Okay. Okay, so 10 minutes? Oh gosh, okay, yeah, so fine. So how would we implement? So let's go back to our resetting. Okay, so I had some process doing whatever, I reset it, etc. A very, very sort of natural way to think about it is via this procedure of intermittent potentials. Here's a process doing whatever it wants in one potential U. I switch it to a potential V, and then maybe there's a resetting there. Then I use that potential to reset. Then I switch it back to U. Okay, so how would I use a potential V to reset? The simplest procedure would be, and the one that we used, is that you just wait. You just wait a few times the relaxation time in the trap. It's going to settle down to a Boltzmann distribution. That's it. I consider that reset. Okay, so of course there was a lot of work done on intermittent potentials from the point of view of steady state properties or even costs, but and I have listed a bunch of papers here. Some of them are in the audience. Okay, Arnab for sure. And this paper where Satya is also involved. So the intermittent potentials, what I mean to say is, have been looked at rather well, but not in the specific sort of procedure that we look at, which is to use the second intermittent potential to reset from the point of view of just letting it sort of equilibrate in the trap. Okay, so here's the potential U, the particle is merrily doing whatever it wants, gets reset. So then if it gets reset, it means I wait for some time, it settles down to its minimum energy there, then I switch off the potential, then it does whatever and so on. So this is the procedure we look at, and I'll tell you in a bit more detail what it is. Before that, I just wanted to say that there are experiments done. Again, a paper in which Satya was involved with Sergio Chiliberto, and they basically consider exactly this process, not from the point of view of thermodynamic costs, but from the point of view looking at steady state or first passage properties. So basically, you have a trap, the particle is trapped. So here's the, so this is time versus the x. And in the red regions, the particle is trapped, it's equilibrated in the trap is switched off, then it's trapped again, etc. In this particular case, the trap is turned on periodically, but that it doesn't need to be. We can, it's just as easy to turn it on with any other schedule. Okay, so our system then, to get a bit more concrete, is defined by this overdamped Langevin equation. Our work is defined. The work, so suppose we are calculating work, the cost I pay is just when I manipulate my trap. That's the cost that I pay, the work cost that I pay. And in the first, so in work that we looked at earlier, we considered, for example, you turn on the trap instantaneously, and you turn off the trap instantaneously. So here I instantaneously went from V to U, then I'm sometime in U. Remember, this is just in the VU space, it's not trajectory space. Trajectory is here. I switch off from V to U instantaneously, stay sometime in U, then I switch it on again. The time that I stay in V is always the same, because it's always 3 times the relaxation in the trap. So these blue lines are always the same. But these red lines could be, of course, depending on the sort of time interval between my resets. So whenever I turn this on, I call it a kind of reset. Okay, so I switch it off, I switch it on, I switch it off, I switch it on, etc., etc. And then the costs here are very simple, because it's just the particle, remember, is an overdamped particle, has no kinetic energy. It only has potential energy. So basically, it's just energy cost here, energy cost here, energy cost here, here, etc. Here it's U minus V, there it's V minus U, here it's U minus V, there it's V minus U, etc. In a long trajectory, I just have to sum the whole thing up. And then I can ask for, so what we could do in earlier work, 2023, yeah, I guess it was published then, yes. So what we could do in earlier work was we could get the moment generating function for the work. I mean, so from there, it was rather easy. We could get the average and fluctuations, etc. But here, so basically, I just wanted to say the work. So we have, a work 1 in the downward arrows, a work W2 is in the upward arrows. So this W1 is here, W2, W1, W2, W1, W2, etc. And then the total work is just the W1 plus W2. We don't have to go into that. So this was just a little aside that, you could use a toy model here. So let me just, I don't know, which would be the best way to see that. Yeah, maybe here. We could use also a toy model to understand some stuff. Maybe there's no time to get into that. I can see a countdown on the screen. So the toy model is just that, okay, so you could, instead of actually considering a trap here, you could just assume that the particle is just directly somehow projected into a Boltzmann state of that trap. So it's a toy model where you somehow abstract away all these traps and everything, and you just say, okay, I just considered the simplest reset process, but now instead of resetting to the origin, I reset to a Boltzmann distribution. And it turns out that, the average costs or, heat, etc., that you can get from there is the same as the average work here, etc. Okay, but that was just an aside, so maybe I should get on. The work which is in progress now is that we have this, we turn off the trap instantaneously. But now we want to turn on the trap slowly. Okay, so because remember, we are interested not just in bounds, but we are also interested in how much time how much, so how this time of turning on the trap affects my work. So basically, I turn off the trap, it's in what we call an exploration phase. I turn on the trap. The particle could be doing whatever. When I eventually have to do an average, I'll have to sum over all possible things that it's doing there. Here, I leave the trap on 2-3 times my relaxation time always. And my system then is a bunch of such processes. Off, exploration, turn on, relax, off, exploration, turn on, relax, etc. And then the process reaches a steady state, in this thing. And now with this scheme, and then I'm interested now in looking at this work cost. And in fact, there was an experiment done even on this. Okay, so more recently by these people here. It's still on the archive. So basically, it's very similar to the old experiment, Besga et al., where Satya was also involved. They still have a particle in a trap. They turn it, and now they, so they keep the trap on for a certain amount of time till it equilibrates, turn the trap off. And now in this experiment, they can turn the, so they have a sort of parameter by means of which the trap is turned off instantaneously, or it's turned off slowly, or whatever. Okay, so again, we have this W1 and W2. Let's say W1 is my instantaneous switch off. W2 is now a more complicated expression. I have to take care of this, the total work where I, in this regime. So just to be a bit more concrete, let's imagine that, we take this f of t, how long it remains in the exploration phase. Let's take the simplest one, which is this exponential distribution. And now, in our system, we have these 3 parameters. There is R times the relaxation in the V trap, R times the relaxation in the U trap, and R times the time that I switch on the trap. There's just these 3, that's it. So the work or anything else must be some function of these 3. So it's very easy to calculate. We can write generating functions and stuff. Even here, it's very easy to calculate an average W2 when I turn on the trap and I turn off the trap. So the W1, when I was this. We can get an average here. And we can get an average work here, which has this simple form in these 2 limits, instantaneous and slow. Now, from our general, equilibrium sort of intuition, you would imagine that slow, if I do the work slowly, it must cost less. But that's not the case, because I'm not beginning from an equilibrium initial condition. Actually, I have a phase diagram. So if I look below the red line, below the red line, all this region 1 and 2 is the region where my U is shallow and my V is sharp, which is what I would do when I'm doing a reset. And then, so in this region, my instantaneous turning on the trap fast actually is, it costs less than turning it on slowly. And here, turning on the trap slowly is okay, costs less. In fact, there's even more to it, because if you look at the work, so you remember work as a function of the time for turning on the trap. This was what we were used to from our equilibrium intuition, and this is the sort of free energy difference at late times. But it looks like, depending on the parameters, it can look like whatever. So you see, at late times, it's always reaching the equilibrium free energy difference between the 2 traps. But at early, here it's doing whatever in between. It can be non-monotonic in different ways. It can be like this. It can be inverted like this. So then the question is, okay, so given all this, like, what could you say about a bound? So this was just the read. So what could you say about a bound? Remember, okay, so I forgot to tell you that these plots were generated with this protocol for turning on the trap, which was also used in that experiment I showed you. Okay, so, now how would you get a bound? Like, in equilibrium, we could say, okay, equilibrium free energy difference. Out of equilibrium, I said that, okay, according to the Esposito-Vandenbroek paper, it should be some kind of non-equilibrium free energy difference. But that's not so satisfactory. We'd like to get it like ourselves, somehow from a procedure. And you can do that via this procedure of optimal protocols. Okay, so we heard a little bit about it from Kiran also in Kiran's talk. This work is a sort of functional of this scheme lambda t. You can, yeah, I'm done. This is the last slide. So this, the work is a functional of the scheme. I can actually minimize this as a function of lambda t. And then I get an optimal protocol. This optimal protocol can be quite strange. It can have sudden jumps and it can be doing various things like that. In the optimal protocol, the slow protocol is always the one that costs least, unlike this other protocol. You see, here is the optimal protocol for some set of parameters. And this is the time for switching on the tap for the trap V. So, at large times, it reaches this dashed line. This dashed line is actually this non-equilibrium free energy difference that we talked about. And then there is this increase. So for the optimal protocol, you see and this is the Tanch protocol that the experiment had used. It's quite far from the optimal. The interesting thing is that this is perhaps a little technical point, and to explain it would take, but I would be happy to discuss it. The interesting thing is that the non-equilibrium free energy difference, so we can actually get from this very simple procedure, actually, which was done by Schmiedel and Seifert in another context between equilibrium systems before, we can actually get an expression for this dashed line as a function of all these parameters. We can see that it's actually a Kullback-Leibler divergence. However, it's not a Kullback-Leibler between the sort of steady state and the equilibrium state. It's something else, okay, some sort of projection of the steady state to the equilibrium state. So we are still trying to understand this. We get a B of tau, but we haven't managed to make the connection between this B and the Wasserstein. We see that it's, of course, a positive quantity, but so that's something that we are working on too. Okay, so basically these were some of the results I wanted to mention, and thank you for your attention.
Thank you. Questions?
Intermediate potential in higher dimensions, for example, 2D or something. Is there any similar protocol there? Or?
No. I mean, that would be the next step, I think. I'm not sure there's that much work in general on that.
No, in general, I mean, except for this one 2D experiment by
that you did with Beska, yeah.
But,
yeah, I haven't seen any other. That would be actually very interesting. That would be the next step. We just wanted to clear up, all this stuff. But it's like after our discussion in Audita, we did this optimal protocol calculation. It's a very clean. It's extremely clean. Actually, we can do the optimization. We are thinking of doing, so we can do the optimization. So we've done the optimization only as a function of this lambda t, which is the scheme for changing on. How do I turn on this potential from U to V? But you can imagine doing an optimization even as a function of this f of t. Like what is the best scheme? Like what's the best time? So that's also possible, I think. That's also another thing that we're thinking about. So we thought we'd clear up all that stuff first before, but that's very interesting. Yeah.
Hi, Supriya. I had a question about the KL divergence.
Yes.
So are you using it to regularize your control, or is it coming out?
It comes out of
It's coming out. You're not putting it in the beginning.
No. So as I said, there's a general understanding that there is a non-equilibrium free energy which somehow includes this KL divergence.
Yeah.
We didn't want to just use that. We wanted it to come out of some procedure. It comes out of this optimization, this optimal protocol. Okay. So we calculate. We are able to calculate an optimal protocol. We are able to calculate a bound from the optimal protocol. And then we can actually see that it's actually a KL divergence. That was actually thanks to Christian had some insights on that. And then we could actually see it was a KL divergence between two states.
That's very cool. So if you can talk about it.
Okay. Well, in the interest of time, we'll stop here and proceed to copy. I guess I'll tell